For our second practical acoustics lecture, I want to talk about transforms. And we've seen transforms quite a bit in the regular lectures applied mathematically. So first I want to say, why are transforms so useful? What is their, why are they our go-to method for solving the wave equation? Well, really, first of all, we see if we take the Fourier transform here, and we're going from the time domain to the frequency domain, we see that, if we apply it to our unknown pressure time series function or our field in the time domain, we simply get the field in the frequency domain. And so, nothing bad happening there. Same thing if we apply the Fourier transform from the time domain to the frequency domain to the spatial derivative of that function. We just get the spatial derivative of the field in the frequency domain. Great, very useful. Doesn't change anything. But the big but here is that if we apply the Fourier transform from the time domain to the frequency domain to the time derivative of our function, we simply get this really wonderfully simple thing here. Omega squared, right? So that's the domain we're transferring to, times the function in the time domain, right? So super, super simple. And then, of course, if you consider the whole wave equation, here's your wave equation. You apply the Fourier transform, and you just end up with this Helmholtz equation. Your spatial derivative's untouched. Your time derivative just becomes a k squared, right? Omega squared over c squared. And here's your p now in the frequency domain. And the nice thing that after lecture, I think 6, you'll see is that if we have a source represented as a delta function, right? So a point source somewhere in space and time, that simply becomes a delta function in wave number in k space. So how useful when we Fourier transform those things. Now, this lecture is called Practical Acoustics, and probably some of you are pretty annoyed that I'm talking about how practical transforms are for solving differential equations. I want to be sort of the opposite of that. So let's talk about Fourier transforms as a tool that takes us from the time domain to the frequency domain. And I want to talk about 3 very simple but very powerful cases to help your understanding of how to use this tool. Okay. The first here is the Fourier transform of Fourier transform of just a sine wave. So in the time domain, right, as you can see over here, this is the time domain. You just have a constant sine wave in the light blue. The Fourier transform of that is a delta function in the frequency domain. So now if we look at that same signal in the frequency domain on the bottom here, you see that there's just a big spike at one particular frequency, the frequency of which that sine wave was oscillating, okay? Now, if we do the opposite of that, now we take the, let me not do that. Now we take the Fourier transform of a big spike in the time domain, okay? That's the red line in the top here. The big spike happens at some time, but if we look in the frequency domain, it just looks like a constant, very, very broadband, constant energy across all frequencies signal, right? So this is just to give you some intuition. When you look at a spectrum, how do you translate that into the time domain and vice versa? Okay, and I've put one more here. I put a little function called rectangle, some rectangle function with some time period, capital T, and that's drawn here in the time domain up top. And then down below, you can see that, interestingly, it looks like a sinc function, sine x over x being the sinc function. But when we take the square of that, it looks sort of like this fringing pattern type function, where you get a spread out version of the delta function. So any signal can be expressed as a Fourier decomposition or as a Fourier series here. And I've written this out mathematically right here. So where I have some time-dependent function, and I've written out as a series of sines and cosines with these Fourier amplitudes here. And so, you can obviously take a whole course on this, but we're just going to go over some things that can help you intuitively. So, we said that if we had a sine wave over on the left-hand side, it would just be a single Fourier coefficient. So you just have n equals 1 and then the sine wave with the right frequency, and that would give you that delta function. So now if we have something like a sawtooth wave, the idea is that you can compute these ANs and BNs using Fourier methods, and then you can come, the solution is actually a series of BNs in this case, for example. And so, it's 1 over n pi. So here we have the spectrum drawn where at each n we have one of these delta functions, and their amplitudes decrease as 1 over n because Bn is proportional to 1 over n. Okay, so that allows you to, sort of look at the wave over here and estimate what it might look like as a series of harmonics in the frequency domain. You can do the same thing with the square wave. And, the nice thing about the square wave, or the interesting thing about the square wave, is that you only have n equals odd harmonics, right? So it looks n equals 1, 3, 5. Now, the one thing to note here is we're looking at the magnitude squared of the pressure. So we could have, a square wave that has been, oops, don't want to do that. We could have a square wave that has some different phase, right? The timing of the square wave is different, but the spectrum is still going to look the same, right? Because we're looking at the pressure squared, so just the power. So when we're looking at any periodic function in the frequency domain, we can tell some of its properties very quickly. So for example, a narrowband function is very narrow in the frequency domain. A broadband function has this, a large bandwidth over which it has energy, but we have to be careful because sometimes we can have a short time. So we take a very small time snippet of a narrowband signal, and because of the processing of that signal into the frequency domain, it will look like a broadband signal, right? So you can see this wider blue smush here. That's sort of the same, they're saying that's the same as the red signal, but we've used a shorter time, lower F resolution parameters to analyze it. So that kind of brings up the question, the ultimate practical question: what are the steps that we take when we're taking this time series into the frequency domain? And so if we're talking about just a continuous time series with a very, very long time series, and that's what we call infinite bandwidth processing, we have, some function x of t, that's our pressure time series. We do the Fourier transform of that. We get a complex amplitude spectrum. We multiply that by its conjugate, or the alternate thing is to take the absolute value and square it, and that gives us something that's proportional to the power. You normalize that properly and you get the power. And then we take that properly normalized version, we take 20 log 10 of that and reference it to a reference pressure, and then we can actually get the power spectrum in terms of dB reference to P naught. Okay, a bit hand wavy there, but you get what I'm saying. Now, in reality, of course, this function is not continuous and it's not very, very long. Usually we have something like this here, where it's the same function, but I put the square brackets to indicate that it's a discrete function. We're sampling it in time, and so it's not continuous, and it has some finite duration as well. So because we're sampling in time, we have some time resolution, delta t, right? That's the time in between each digital sample, and that's inversely proportional to the sampling rate being, the rate at which you're taking those samples, some samples per second, or hertz. And this time series x is usually sort of n samples long, or we can take an n sample segment of it, which corresponds to some time in seconds, capital T long. And from that, we can compute the frequency resolution, which is equal to 1 over t, or 1 over delta t times capital N. And that gives you your frequency resolution, which can influence what the signal looks like in the frequency domain. Now, one of the things we do to trick ourselves, to trick each other into kind of improving the resolution in the frequency domain. You're not really improving the resolution, but you're taking care of something called spectral leakage. And so if you have your time series here, that's very noisy, and you take some chunk of that time series, you can multiply it by something called a window, and that's just sort of this tapering function here, where this is time, and it goes to 0 at the beginning, at the end of each of your at each chunk that you analyze. So if we cut this out and then move it over here, really using the technology. And now I want to apply the windowing function as well. So now this is going to be changed, and it's going to have all the, and go to 0 here. It's going to have all the wiggles in the middle, but go to 0 at each end. So the envelope is going to reflect that windowing function that we used. Well, then what happens is when you compute the Fourier transform and then compute the power, you're reducing what's called spectral leakage. So something to do with how you chose this length t can influence how the power stays in the different frequency bins. And sort of one of the results of that I've sort of drawn here is, you have your unwindowed black line and your windowed blue line. You can see that you're able to resolve these peaks a little bit better when you window your function, because you're reducing how much the energy spreads out in the frequency domain. So you're not really improving your resolution in F, but you're improving how you look at your, how your function behaves during the processing. Now, one more thing I wanted to talk about was just the idea of taking your power spectrum, computing it in time, and computing a spectrogram. So something we all have a pretty good idea of how to look at, and we know it's one of the most useful ways to visualize time series data. I just want to say a few words about that. So the typical idea is that you have your pressure time series here, so some long time series, and you split it up into these different chunks. So I've got 1, 2, 3, 4 chunks. You compute the spectrum for each chunk. So here I have one with no signal in it, and then sort of chunks 2 and 3 have this little bump that comes from this signal here. And then you just simply line these all up and plot them 1, 2, 3, 4. And you can see, okay, it's just a way of visualizing the data and seeing this little bump in time, which is related to this signal. And so we can also play some games to improve our how these spectrograms look, right? And so, for instance, you can choose your chunks as overlapping chunks. This could be chunk 1, and this could be chunk 2 or segment 2, and etc. 3. And on. And so then that would allow you to have more estimates, more densely spaced estimates of what that spectrum looks like as it evolves through time, and getting a sort of a more detailed picture of the spectrogram. So obviously you could take a whole multi-year course on time frequency analysis, but here we're just giving a quick overview, some useful things that might be practical in this practical acoustics lecture.